Hi, I'm Alex, and I'm here to talk about the instrumentation amplifier because it can look a little bit intense at first, but by breaking it down into its component parts, I think we can get a good grip on how this circuit really works. So first of all, the instrumentation amplifier is a circuit, a specific configuration that contains this is the instrumentation amplifier part, and it contains three operational amps. So you can see these three op amps here. And that's how we're going to kind of approach understanding this circuit, is by taking what we already know about op amps and applying it to this configuration. So this is our instrumentation amp, and then we're sending in two signals. We have a reference here and a measurement electrode. So here, this reference is picking up a 60 hertz sine wave, which is supposed to represent noise, like 50 or 60 hertz that you would encounter in the lab. It's got an electrode, so the electrode has some impedance that it has to cross in order to actually enter the instrumentation amp circuit. Here we have our measurement electrode, which also picks up that 60 hertz noise. But now, in addition, we also have this little square wave at 120 hertz, and that's representing our action potential. So they also go over a bit of impedance. These impedances are really different, just to show you that in this configuration, it doesn't really matter. So this also goes over electrode impedance and then enters our instrumentation amp circuit. So what we want this to do is to say, right, we've got a 60 hertz noise on our reference. We've got the 60 hertz here, and actually the action potentials in terms of amplitude are so small that you can only just see them in this tiny little wiggle here on top of so much noise. And what we want our instrumentation amplifier to do is to subtract the 60 hertz noise from this signal and leave us with only the action potentials. And if we look at the out signal here, we can see that it's doing that really successfully. It's only outputting these little square waves here. So that's what it does. Now, the second question is how it does that. And to explain that, I'm going to make two changes to the circuit. First of all, I'm going to get rid of this, what's called the gain resistor for now. And what that does is kind of separates our stream into a reference stream and a measurement stream until we get to that final operational amplifier. The other thing I'm going to do is get rid of these sine waves and change it into steady voltages. All right, so that would look something like this. I changed it into a steady 1.1 on our reference electrode and a 1.2 on our measurement. So this is a very boring, useless experiment, but you're measuring a constant difference of 100 millivolts between these 2 points. So let's see what our instrumentation amplifier does with that. Just visualize the output here. Okay, so we can see that we're sending in a difference of 100 millivolts, and the amplifier is doing a very good job of almost perfectly outputting 100 millivolts over here. So how does it do that? Well, we can understand it by applying what we already know about operational amplifiers. So we know two things about op amps. First of all, they have very high input impedance, which means no current can travel into the terminals of an operational amplifier. So no current is ever allowed to go in here or here. Secondly, all these amplifiers are in a negative feedback configuration, which means their output is tied to their inverting input, which is this minus sign here. So you can see that every time there's an output, it will make its way back to that minus sign, to that inverting input. So what this negative feedback configuration does is make sure that the operational amplifier will output whatever voltage is necessary to make the inverting terminal have the same value in terms of voltage as the non-inverting terminal. So it will read whatever's coming into this plus sign, and it will output whatever is necessary to match the minus to the plus. So what we're basically doing is saying, there's a voltage coming in here, and we want that same voltage to be replicated over here. So let's just see if that works. If we follow our reference signal from here, so 1.1 here, we've got quite a high impedance, 100K here, but that will be negligible compared to the super high impedance of our amplifier. So because this is so high, we get a voltage divider where this value, it seems relatively low. And that means we'll have a very low voltage drop, so we should have the same value here. Yeah. So almost no voltage is dropped over this value, so the impedance of the electrode becomes way less important than it would otherwise due to the high input impedance of our amplifier. So we've got 1.1 coming in here, and we would hope that the amplifier is making that this is also 1.1. Yeah. All right. So now we've got a replication of the voltage coming in on the other side. And let's just check that's true here as well. Yeah, 1.1 and 1.2. So these two amplifiers are really acting as buffers, which means they take one value, they replicate it on the other side. So from now on, rather than your entire acquisition system being driven by your neurons, by your electrode, you're providing a new source here that will power the rest of your system. So this 1.1 is not fragile, it's not dependent on the output impedance of your electrode anymore, because it's based on the super low output impedance of your amplifier, and your amplifier can provide lots and lots of current. It's a much more powerful and flexible source. Okay, so we've got our replicated voltage here. Now these two voltages, so there's got 1.1 at the top, 1.2 at the bottom, these are the ones that's actually going to get fed into this final amplifier. And this is the one that's really going to be comparing the two and subtracting the difference. So how does it do that? Well, if we just get rid of it for 1 second, all right, I've just moved the amplifier and added a little ground, and that will allow us to visualize the voltage that this final amplifier would be receiving at like t is 0. So at the very first, if the amplifier wasn't there, we'd be getting a 550 at the top and a 600 millivolts at the bottom. And that's because we have a voltage source here, again, sourced by the amplifier now, and it's in between two identical resistors. So these are forming a voltage divider, splitting our voltage in half, both at the top and at the bottom. Now, if we put our amplifier back in, we can see that it's successfully driven up the voltage here to 600 millivolts, making these two guys match. And how much would it have to do that? So it's going to go from 550 to 600 millivolts. So it needs an extra 50 millivolts over here. It's, again, this output is in between a voltage divider. So it's actually going to have to output 100 millivolts in order to get a 50 millivolt increase over here. So to get these two to match, it has to output the difference between the inputs we actually sent it. We're sending a constant difference of 100 millivolts, and we're getting a constant difference of 100 millivolts out. This only works because the voltage divider is present here and present at the bottom. Okay, so let's put that gain resistor back in. So if we put a resistance here, I'm going to start with a very high value, something like, I don't know, just lots of zeros. What's the difference between having this resistor and not having this resistor? Well, you can see the output is 100 without it, and it's 100 with it, and the current also looks very similar. So this is pretty much the same, and the reason for that is that the impedance here is so high that almost no current is allowed to cross it. It's basically the same as having a big air gap here. There's really no difference. So if we have a very high value for this gain resistor, we maintain that one-to-one relationship between the input, 100 millivolts, and the output, 100 millivolts. If we decrease the resistance here, make it something more like 1K, now we can see a difference. We're outputting 2.1 volts, which is much higher than before. And really crucially, we're getting a current running across this part of the circuit that we didn't have before. If they're separate, remember there's no current allowed to go into these op amps. So there's no current allowed to run through this whole part of the circuit. But if we connect them, suddenly we do get a current running across here. And this changes the amplification of our circuit. So this actually introduces like a multiplication factor, which is our gain. So how does that work? Well, we can apply the same principles we did before. No current is allowed to go into the op amps. So we can still see that that's true. There's no current running here or here. There is current running here. And the second thing, op amps will do their best to make that minus terminal the same as the plus. They're still succeeding, clearly, because 1.1 here, 1.1 there, 1.2 here, 1.2 here. But now that there's a current running here, they're actually replicating that voltage at a slightly different point. So before, there was no current running across this resistor, so there was no voltage loss. Just following Ohm's law, if there's no current, there's no voltage drop over this resistor. Now there is a current running across it, which means there's going to be a bit of a voltage drop here and here, which means the value of voltage that we need at the kind of output of our amplifier is going to be different. You can see that now we've got a 2.2 volt here, because some of that voltage is being lost here, and that's the value that we need in order to get 1.2 at the actual inverting terminal of our amplifier. So if we take it away again, you can see no current, no voltage being lost, 1.2, 1.2, 1.1, 1.1. As soon as we introduce this, we have a voltage drop, which means that we have 100 millivolts here and a 2.2 volts here in order to get those values that we require at the inverting inputs. And what that means is this second amplifier is actually receiving values that are much more separate than they were before. Before, they was actually receiving that 100 millivolts difference. Now that difference has kind of been stretched, where the inverting and the non-inverting terminals of the final op amp have more separated, more distant values than they did before. So another way to think about it is this amplifier is doing whatever it can to get 1.1 volts here, which means here, this point has to have 1.1 volts. Let's just show that. Whereas the other amplifier is making sure that this is maintained at 1.2. So there's a potential difference of 100 millivolts over this. As long as the amplifiers are doing their job, this will be true. We have a potential difference and we have a resistance, which means that following Ohm's law, we're going to have a specific current. So maybe we can just visualize that current as well. We've got 100 microamps going along this. Now the current coming into each point of the circuit has to be the same as the current coming out. There's no current going on here, so we don't have to worry about it. It does mean that we have to have the same amount of current going over all these three resistors in the circuit. So because we have that potential difference and that 100 microamp current here, we have to have that 100 microamp current going across this whole part. So basically these two, this 2.2 and this 100 millivolts, is what those two buffer op amps have to output in order to get to compensate for the voltage drops that they're going to experience and have that due to that current running across it. And that can kind of maybe already show you why this is a gain resistor, because if we make this value lower, we reduce the resistance. The potential difference is the same. It's still at 100 millivolts. So that means we're going to get a higher current. Same voltage, reduced resistance, higher current. Because we have a higher current running over these resistances, we're getting a bigger voltage drop. So the amplifiers are going to have to compensate even more in order to get those values that they want here. So when I make the gain resistor lower, I'm increasing the current, I'm increasing the voltage drop, and I'm telling the amplifiers that they're going to have to work even harder to act as buffer amps and to replicate those voltages. Now, if we move that final op amp out of the way again, we can kind of see at T is 0. Before we had a difference of 50 millivolts. Now we have a much bigger difference at 1.6 volts on this side and minus 500 millivolts on that side. So that is what that final operational amplifier is seeing. And it will therefore have to send a much higher output in order to get this inverting terminal to match the non-inverting terminal. And as we can see, it's outputting 4 volts, which is way higher than the 100 millivolts we're sending in. This already can show us one of the things that can go wrong in this circuit. So what if we make this really, really low? So we're saying only 100 ohms, which means we're going to have a very high current flowing through this part of the circuit. You can see this is getting very dark red and this is getting very light green, or you can read the values here, 11.2 volts and minus 8.9 volts. So let's again see what we're asking. We're saying, okay, can you output enough to make this point, minus 4.4, equal this point, 5.6? That's a 10 volt difference we're asking our final amplifier to deal with. You can see that it's not quite succeeding. It's bumping it up a little bit. It's getting it to 3.1, but it's not getting it all the way to 5.6. And that makes sense because this final amplifier is driven by two voltage lines, a minus and a plus 15 volts. It can only output 15 volts. We were asking it to compensate for a 10 volt voltage difference, however, in the middle of a voltage divider. So to get that 10 volt increase here, it would have to output 20 volts, and it can only ever output 15. So this guy is saturating. It's not outputting anything. If we increase or change this difference here, we won't notice any response because we're working in the saturated range of this amplifier. So we can maybe show you. Yeah, this is not representing any change. We're making the difference bigger, but we're not seeing any result of that in the, we can make it a lot bigger in terms of the output. So let's bring it back to our 1.1 and 1.2. So that's one thing that can go wrong. If you're asking for too much gain, your final amplifier here will saturate. If we put this back to 1K, now it's fine again. We should see that if we change this voltage, we'll actually get a corresponding change in the output, which we do. Another thing that can go wrong might help us understand why we need to make sure we're grounding properly. So the thing we always say about instrumentation amplifiers is, oh, they're really good at taking the difference in the inputs and only outputting that difference, not whatever signal those two share. So sometimes you may think, okay, if it's only outputting the difference, then it's fine if I put the reference at 100.1 and the measurement at 100.2. Now this might sound a little bit over the top, but it's actually quite easy to do. If you're not grounding your setup, your animal or your setup could easily be a lot higher in terms of just direct voltage than your ground. So say we've done something inadvertently not so smart and we haven't grounded our setup properly. So we haven't provided a low impedance path to ground, allowing any excess voltages to kind of escape. So basically our animal's sitting at 100 volts higher than our ground. And this is relevant for anyone, even if you think, oh, I've got like a floating system. You may not be connected to Earth, but you always have to have a ground. There has to be a point in the circuit that you have decided is 0 volts. So if you have 100 volts difference between your setup and ground, why is that a problem? Well, you might think, I'm only interested in the difference anyway. The difference is 100 millivolts, whatever, this should work. But if we run the circuit, we see that we're getting a 10 microvolt difference out, which is not what we're looking for. So something's gone wrong here. So I think the easiest way to understand it is to just look at these buffer amplifiers and remember what we were asking them to do. We said your job is to take this input voltage and replicate it here. As long as you're doing that, that's great and it's working. The amplifier is doing its best, but again, it's only allowed to output 15 volts, and that's what it's doing, and it cannot raise that voltage any higher. So as long as either of these are sitting at higher than the range of that those first buffer amps, you're going to get saturation. So this final amplifier isn't comparing any useful difference. It's comparing the difference between the saturation values of these two amplifiers. So it's outputting basically nonsense. So this is why you want to ground these. You want to get rid of this really you want to get it more like this. You want to get rid of this this constant offset between the two and get it back into a range that the amplifier can deal with. Because we saw before, if it was 1.1 and 1.2, the amplifier was fine. It could cope with that because it could replicate those values. So even if it was probably like 7.1 and 7.2, it'd be fine. Yeah, it can cope with that. It just cannot do anything over that 15 volts because then it will be saturated.